So far in diffusion, facilitated diffusion, and active transport, we have focused mostly on the movement of solutes in and out of cells. It's hard to remember that at the same time solutes are diffusing down their concentration gradient, solvents are also diffusing down their concentration gradient. The most common solvent around in cells is water, and the water is always moving in the exact opposite direction that the solutes are. Since in a normal person, 70 to 85% of our cells by weight are made of water, it's the diffusion of the solvents that's often most important to a cell's survival. For this reason, scientists give it a special name, osmosis, which is the diffusion of water down its own concentration gradient. To understand how osmosis works, let's imagine for a moment that we have a beaker of water with a selectively permeable membrane right down the middle of it. And then on one side we place a whole bunch of solutes, and on the other we only place a few. As you guys know, molecules move from areas of high concentration to low concentration, and so if they could, the solutes would end up moving in this direction. However, this membrane down the middle is selectively permeable, and in this case, let's say that it is impermeable to solutes. These large sugar molecules that are floating around cannot make their way across the membrane. Well, sugar molecules are pretty sizable, like perhaps this is glucose. That's 24 atoms large, that's pretty big. Whereas water molecules are super small, they're just H2O, which means that they're very likely to be able to fit across a membrane. So even though the sugar molecules can't diffuse down their concentration gradient, water can. And the water is more concentrated on the opposite side of the glass, with just a few molecules on the other side. So if water is permeable to the membrane, it will move in this direction. In this scenario, we will get a beaker of water that looks something like this. Since the membrane is permeable to the water only, the water moves to the left side of the beaker, whereas the solutes stay put. And so you end up with this uneven situation where the left side of the beaker has a lot more water than the right side of the beaker does, because the water is moving down its concentration gradient, and does so much that it can even fight gravity, and part of the water will go up on one side even though it's lower on the other, and they look uneven. Now, scientists are lazy, and they never want to say any more words than they have to, so of course they invented some terms to describe these different solutions. So if you have two solutions, the one that has more solutes in it is known as hypertonic to the other solution. The root word hyper means a lot, and in this case, a hypertonic solution has a lot of solutes compared to the other. Then on the other side of the beaker, we have a hypotonic solution. So the fancy way that a scientist describes osmosis is that during osmosis, water moves from the hypotonic solution, where there are fewer solutes but more water, to the hypertonic solution, where there are more solutes but less water. So let's add to our definition. Osmosis is the diffusion of water from hypotonic to hypertonic solutions. This is because in the hypotonic solution, though there are less solutes, there's more water. Meanwhile, in the hypertonic solution, there's more solutes, and so there's less room for water. So the water, just like any molecule, will move down its concentration gradient from the area where it's more concentrated to the area where it is less, even though the solutes could be doing just the opposite. What does this look like in the context of cells? Let's pretend we have a little cell right here in the middle of a beaker now, and that the inside of the cell is hypertonic to the outside of the cell, which is hypotonic. And you can see that because there's just a few little solutes floating around out here, whereas there's many solutes inside this cell. If the membrane is selectively permeable, and it does not let the solutes in or out, but it does let water in or out, then here's what would happen. Water would osmose into the cell until the cell got as big and huge as you can see it is down here. Water will keep moving in and in and in until the concentration of solutes both inside and outside of the cell look equal as they do in this picture. Look, now they're just as spread out inside as they are outside. At that point, the two solutions get a new name. They're called isotonic. Isotonic solutions have equal concentrations of solutes. Now, this osmosis of water can actually be pretty dangerous for cells. For example, if I put one of your cells into some pure water, meaning a very hypotonic solution, its cytoplasm, of course, has plenty of solutes floating around in it, which means that the water will then, by osmosis, start moving into the cell. And this movement inward could continue and continue and continue until there's so much water inside the cell that the cell bursts, or in fancy scientific terms, it lyses. This is what occurs when somebody, on rare occasion, drinks too much water and they die of water poisoning. It's because there's so much water inside their body that the water is flowing into the cells at such a rate that cells start to explode. A rare condition, but it is possible. It's much better that you drink just enough water so that there's equal amounts of water inside and outside your cells in your body. Between these two isotonic solutions, water will be leaving the cell at the same rate that it is entering the cell, and so the cells will stay approximately the same size. There's a third possibility, though. What if your cell is placed inside a hypertonic solution? So that means more of the water is inside and less of it is out. That means more water will be leaving than will be entering, and the cell will end up shriveling and dying in that way. This could happen if you go jogging and you don't drink any water afterwards and you start feeling super dehydrated. That means some of your cells might be kicking the bucket and becoming so shriveled that they die. In other words, you want to drink enough water that you keep an isotonic solution outside of your cells at all times. You don't want to get dehydrated so that the cells become hypotonic and the outside becomes hypertonic, because then the water will start leaving your cells, causing them to shrivel and die. In this third condition here, it looks much the same in plant cells as it does in animal cells. You can see this poor plant cell. It's got its nice sturdy cell wall around the outside, but if water is leaving the entire time because the cell is in hypertonic solution, then the poor cell membrane shrinks away from the cell wall, and you get a dead cell by plasmolysis. A plasmolized plant cell is not doing very well. And if all of the cells in a plant are in this condition, then that plant is really unhappy and it's wilted and probably dead. So don't forget to water your plant cells. Plant cells are a little bit different from animal cells. They actually prefer being in a hypotonic solution. So this is their favorite place to be. If there's tons of water outside, then all of that water is diffusing in and diffusing in. If they were an animal cell, yeah, they might burst, but they're not. They're a plant cell, and they have a cell wall around the outside which protects that balloon-like cell membrane from expanding and expanding until it pops. So a happy plant cell is actually one that would pop in the absence of its cell wall, but since the cell wall is there, it protects the cell from exploding, and instead the plant stays nice and rigid and can stand up straight. If a plant cell is in an isotonic solution to itself and water is leaving at the same rate that it's going in, the plant is okay, not the best. Generally, we call that flaccid. So in that case, the plant is starting to wilt. Those leaves are starting to look a little meh, not so appealing. It's kind of like if you've left a carrot sitting in the fridge for a really long time and then you pull it out and it's sort of droopy, then it might be at this point that enough water has left that there isn't the pressure inside the cell to hold it nice and strong. So plant cells, in conclusion, prefer to be placed in a hypotonic solution, so you could just take that carrot and stick it back in a little bucket of water and put it back inside the fridge, and then eventually more of that water will osmose into the cells until the cells become turgid again, and then you'll have a nice crunchy carrot instead of a sad, wilted, flaccid carrot. So, in conclusion, osmosis can be just as important, if not more important, than active transport, facilitated diffusion, and diffusion, because water molecules are the most common ones inside and outside of our cells. So depending on the kind of solution that a cell finds itself in, the direction that water is osmosing can greatly affect that cell, either to make it shrink and die, or to make it explode and die, or if the solutions are isotonic, it can keep that cell nice and healthy.